Okay, this is the third and final podcast of our Unit 3 packet. So we're going to be finishing up our packet next class, reviewing a bit, and we're going to be testing next week. So, let's make sure our packet is up to date. Pages 9 and 10 are going to be our goal, and after that, there's just a couple pages of practice. So, let's get started. Now, our next trend that we're talking about here is electron affinity. Electron affinity is a measure of the energy released when an atom gains an electron. Now, that might sound a little bit weird, but really, this tells us how much an atom wants another electron. It's kind of like if I give two people candy, I can tell which one likes that candy or wanted candy more by how much energy they release and how excited they are from getting that candy. So, this is an important measurement for how atoms form bonds. And that's what we're measuring, is the amount of energy released. So we're going to write this equation to show this energy being released. Make sure that goes up kind of next to where it asks you to write the equation, because we are going to have to summarize the periodic trends and the group trends underneath that, and we need to add those in there. So quick word about this equation. I'm not going to ask you to write these in the future, but this just shows fluorine adding an electron to it. And when fluorine becomes a -1 charge, after gaining that electron, it releases this energy. What I wanted to point out is that this is a positive sign, even though this is a negative sign. Here, that negative means that energy is being lost or being given up by fluorine, but we never have actual negative signs in our chemical reactions. So just introducing that idea early. We're going to study chemical reactions and their energies a lot later next semester. So that's our equation there. Now, as we talk about the trends for electron affinity, remember, periodic trends, meaning the ones in a period or row, the nuclear charge is the major change that's happening in the atom. As we go across a row, the nuclear charge is increasing and making a stronger kind of magnet at the center of my atom, which means because that nuclear charge is pulling harder on the electrons, the electron affinity, how much that atom wants to attract more electrons, is going to increase. In a group, we're increasing the shielding as we go down, more and more energy levels, making our electrons farther away from the nucleus, and less attraction to that nucleus because of the distance, means that the electron affinity, the ability to attract or the desire to attract that electron, is going to decrease. So, we're going to summarize this trend real quick, and I know that there's that periodic table there. You could probably draw these arrows on that. I'm going to keep drawing my little example periodic tables off to the side, but when it comes down to us, we said this in a row, our electron affinity is increasing as we go from left to right. So that's the direction we're going to draw our arrow, but we just said that it was decreasing as we go down a column. So I'm going to draw my arrow pointing up this time. And these arrows look a whole lot like those ionization energy arrows that we drew before. And they're pointing over there, and it looks like helium would have the greatest electron affinity. But if you look at this table, this shows that helium and all the other noble gases have 0 electron affinity. And that's because they don't want electrons. They're happy with the electrons that they have. So we're actually going to be excluding the noble gases from this trend, which with the same arrows that we're looking at now means the highest up and over element with the greatest electron affinity is going to be fluorine. So fluorine has the greatest electron affinity, means the closer we are to fluorine, the larger that electron affinity will be, except for the noble gases. No matter how close or far they are from fluorine, they have 0 electron affinity. So we're now going to talk about electronegativity, which seems like the same thing. It's a measure of the atom's attraction for electrons, but this is when those electrons are in a chemical bond. Because in bonds, our electrons are shared or transferred and may move around, and even though the electrons might supposed to be shared between two atoms, certain atoms might hog those electrons more because they have a greater electronegativity. So they don't always share equally. This will tell us who is going to be hogging those electrons. But before we get into that, knowing that this is an attraction for our electrons, there's a couple of questions about how these two trends relate to each other, ionization energy and electronegativity. And you are going to be responsible for knowing how these relate to each other. But you're going to be giving us answers like this. Elements with low ionization energy have low electronegativities. You're not going to have to analyze quite as much of the how or why, but it is important to understand the why so that we can get this part down. So I'm going to help you with this first one. Elements with low ionization energy, that means that it's easy to remove an electron from them. It's low energy, easy to do. That easy to remove because there's less of a nuclear charge pulling on those electrons. More shielding or less protons one way or the other. So they're not going to be pulling very hard on electrons in the chemical bond either, which equates to a lower electronegativity. So these all come back to the electrons, and it's easy to kind of take it systematic. What is this? What does this mean? And how does this relate to what this other trend means? So I want you to try and do that for this next question. That is basically the opposite. Talks about elements with high ionization energies have high electronegativities because why? Use our answer to the first question to help you model and finish out the second question answer. I'm not going to stamp you unless you have a good answer down here. So that's electronegativity kind of basics. Now let's get into the trend on the next page. Periodic trend for electronegativity. Remember, nuclear charge is what's changing. So that increased nuclear charge is pulling harder on the electrons, which means the electronegativity, the amount that this atom is going to hog electrons, is going to increase. And in the group with more and more shielding as we move down an energy level, the electronegativity is going to decrease because they don't have as hard of a pull on those electrons in their chemical bond. They can't. There's shielding between the nucleus and those bonded electrons. So that's our trend. We're going to skip the practice problems real quick and come down to summarize the trend. There's actually not a whole lot of room to summarize it here. So we're just going to put this in the area where we're going to summarize all of our trends. Just make sure that your little periodic table doesn't take up a whole lot of room because we're going to have to summarize the other three trends here as well. So electronegativity, like we said, it increases as we go from left to right in the period in a row. It decreases as we go down the periodic table, so the largest electronegativities are at the top. And as you might have guessed, the noble gases, because this is talking about forming chemical bonds, they don't form chemical bonds. They don't react. And so we're going to exclude them from this trend as well. Anything to do with electrons, electron affinity, and electronegativity, we're excluding the noble gases, which means that just like our electron affinity, fluorine has the highest electronegativity. The closer to F we are, the larger our electronegativity is, except of course our noble gases. So that's our trend. Now let's use that to do a couple practice problems. And I know there weren't practice problems for electron affinity. The answers would be the exact same as these. These two trends are basically identical. The only real difference is in their definitions. So you can almost kind of treat both of these like one trend. So these ask us to arrange these elements in increasing electronegativity. So first, find our elements. And then we need to remember that the biggest electronegativity is fluorine. So that's part of our sequence there. So if we're arranging them in increasing order, remember, that means small to big. Increasing doesn't mean start with the biggest ones. So I need to find my smallest electronegativity, and that one is actually kind of also a little bit of a trick. It's going to be our neon right over here because it's a noble gas. It has 0 electronegativity. So even though it's sitting there right next to my biggest electronegativity, noble gases have 0. So that's always, if you've got a noble gas, that's always going to be the smallest one in your electron affinity or electronegativity. And then we're going to go as far as possible away from fluorine to start the rest of our ordering. So that would mean going to Na, and then getting a little bit closer and closer each time until we get, of course, to fluorine, which is always going to be the largest electronegativity. Make sense? This is a little bit weird and twisted because of those noble gases, but as long as you remember anything to do with electrons, those noble gases are 0, you're good. So in this next set, got to make these answers disappear so that I can look at these next set of elements. Another row, we have another noble gas there. So increasing order, we're always going to start with the smallest. Noble gases always win that. And then Na again is second, very low electronegativity, Mg, S, and Cl. So I want you to try this next one. I'll go ahead and point out what the elements are in here, all in the same column. Go ahead and try and put those in increasing electronegativity order. There's no noble gases there to throw you off, so it should be a pretty simple order. So that's where we're going to be done for practicing, and now we're just going to go back down to where it said to summarize all of our trends. And I'd really like it if you could get all of these trends together. If you wanted to combine these two trends, their periodic tables together, you could just label this as electron affinity and electronegativity. Then you could definitely do that, and that way you would only have to draw 3. I've drawn these before with all of them layered over the top of each other, and they get really messy and confusing, so I really do find that drawing them separately really helps keep it clear. And that's what we need to be working on, is keeping these 3 different trends. What are they? Which one is the biggest, so that we can put things in order or select the biggest or smallest value. Like, that's what you're going to be doing on your test. It should be pretty straightforward. So that's it. That's our unit. All done.